Is it cloudy or is our future clouded? Where does it come from? And if you look at it, it's really the changing face of use of HPC. High performance computing, I'm known to have said in this room, use words like dinosaurs and extinction before. But even in the short span of the last 5 to 7 years, the use of high-performance computing for more than just the traditional modeling and simulation, the world of partial differential equations, and things like Navier-Stokes, and those kinds of things have expanded to a much broader set of things beyond science, beyond national government missions, to literally becoming the economic scaffolding of the digital economy. I have a few examples here. Smart economics. Unfortunately, HPC can't make smart policymakers, but they can certainly provide the tools to actually have intelligence, the predictive capability, the analysis capability then drives that predictive capability into actually managing monetary systems with reduced risk, right? Everybody says it's an art. It still is an art. But it's a better informed art now thanks to the tools of data analytics and even artificial intelligence that feeds in many of the information streams and takes from that data insight for us to manage large, complex scale interactions in economic models, in financial models, in monetary models. The other one is autonomous driving. We've talked about this before. I've talked about this before. I said here last year that the race to exascale would be won by an application that will touch all our lives, and that would be autonomous, some form of autonomous or smart driving, and that would be transformative on the industry, on the world, and society, because I claim that my children may be the very last, and your children may be the very last, generations to actually learn how to drive. So that keeps going. Smart factory. This notion of actually an instrumented factory, and a factory that is not only more efficient, but that is self-healing, that actually knows, like a bunch of human beings hired to keep it going, keep it operational, and improve its capabilities, that's all done by machines and their intelligence, all enabled by the analysis and predictive capabilities that high-performance computing can build. The last one is predictive analysis on this foil. It's certainly the last one on this foil, but I could go on and on and on about where that fundamental basis or fiber of being able to look at data, being able to correlate, to be test models, build models, predict against those models, and iterate happens. Predictive analytics. Unfortunately, it's a sports analogy here, or a sports example here. It still cannot fully tell you whether your favorite football team, or in my case, favorite cricket team, will actually win. But what it can do is improve performance of players, improve performance of teams, so it can certainly be used to improve the sport, but at the same time, it has a much broader effect. Think of the whole betting industry around sports, right? They now have a different tool. I'm not going to pass judgment on the whole area, but they now have a different tool to add insight into how that entire multi-billion-dollar industry is driven. Again, all on the backs of HPC, right? So if you look at these new uses for HPC, you have to ask if this is where the future is, and it's no longer just restricted to the science and national missions of the past 20 years. What's going to happen? Is it simply going to be down the path of more performance? We come to conferences like this, we look at breakthroughs in hardware, we look at breakthroughs in software, we look at breakthroughs in usages. We also look at breaks, things that break, right? And is it simply going to be the same? I contend that the future is slightly different than taking the last 5 and simply predicting forward, right? It doesn't take HPC to say that. What is happening, if you notice why I said that, a lot of these exciting new usages, a lot of these capabilities, a lot of this experimentation, and a lot of the economic benefit is actually happening in the cloud, right? I don't want to belittle very large supercomputing centers in the world, right? They're there, they get regular upgrades of technology, they do their missions expand. But that is what we've come to know and expect. What you wouldn't expect is names like Amazon and Google, right, actually becoming HPC powerhouses. I try to do a little basic math in my head. I know that's a dangerous mission. But I mean, from what Amazon has stated publicly that they have in terms of server capacity and power, and kind of the state of art of compute density that companies like Intel can provide, they would easily be more than the #1 system on the top 500 by far, right? So clearly the capacity exists in the very large public cloud service providers, right? And they are rapidly becoming the data hosts, the data lakes, that facilitate much of these new uses. NASA uses Amazon's web services for large image analysis, right? How many people would have thought, hey, that quote-unquote partnership or relationship would happen, and would happen this quickly for such a core mission for the agency? Most people, you can read for yourself, most people will tell you that the only way to get to connected cars and then post-connected cars to self-driving cars is to actually have a cloud-based infrastructure where there is a central place of intelligence. This is where the training happens, where the data repositories are, where the learning is progressed, and then all of these millions or hundreds of millions of cars run autonomously based on this infrastructure in the back end, right? And then the last one is akin to the smart factory example is the Internet of Things. There are many more things than there'll ever be people. And someday they will work together to be as smart as people, if not more, right? That is the future we are facing. That is the future that's unleashed by this capability, by this delivery mechanism called the cloud, right? I know many of us have looked at it or have spoken I started this journey into the cloud for myself about 5, 6, 7 years ago. And I'll tell you a personal story. I first thought very similar to when x86 entered the server space, right? It was seen as, oh, that's just your personal computer CPU. How can that run a mission-critical server, right? About 6, 7, 8 years ago, that's the way we collectively, I think, and many of us, I shouldn't generalize overly, looked at cloud. It's a hyperscale, lowest common denominator, multiple things. They really don't understand HPC is very specialized. It's the other thing. If you want to go look at your Facebook pictures or do something, please go to the cloud. But how can you run HPC in the cloud, right? That myth, personally for me, as I've journeyed through this space, has been broken, and I think it's been broken, busted for much of the industry, which is why you see some of these gigantic advances happening from the cloud service providers and the cloud technology, not just the people who are serving them, but the technology of the cloud in making these new uses happen. So, in a nutshell, the future is extremely exciting based on how many more things high-performance computing is going to be used for. And the second thing, as you say that, must be, and the way to deliver it won't just be the way it used to be. The cloud is central to the delivery, to providing the reach, to providing the capability for those things to happen, right? That's why I said cloudy future. I actually forgot what I said on the title. What did I say on the title? Clouding the future. But if you notice, I had a question mark at the end of it, right? I didn't just say clouding the future. I said, is it clouding the future? I didn't mean, is the cloud in our future? I really meant this gigantic change that's slowly but steadily and now rapidly happening is, how are we going to deal with it? How, as a community, are we going to deal with it, right? These are numbers from our own market analysis of the growth of high-performance computing. The dark, if you see, am I going to blind myself? No. The dark is what I call HPC on-premise. This is our traditional HPC, right? And the light blue is the HPC that's delivered from a cloud. It could be a private cloud. It could be a public cloud. In most cases, it is a public cloud. Right? If you look at the growth, obviously with all of those new users coming online, the on-premise is growing. But the HPC delivered through the cloud, and this you can think of as compute units or CPUs, if you will, is growing at 2x the rate of what it's growing on-premise. So the majority of the faster growth of HPC is happening in the cloud. And by 2021, 30% of the CPUs, or compute units deployed for the cloud, we believe, for HPC is going to be in the cloud. Think of that for a second. I remember being if it was not supercomputing at an ISC, it was in Leipzig. How many of you were in Leipzig? That beat Frankfurt this week for high temperatures, I think. Where we said maybe 10%, 15%, right, or some low number. And in a rapid couple of few years, we've ratcheted it up to 30%, just based on what we are seeing are two things: actual deployments and what people's intent are based on the value proposition of a cloud infrastructure, right? If you look then at what the cloud does and start addressing the question of the question mark, if you look at it and say, is cloudy a negative judgment? You have to ask, what is changing, right? The fundamental change, we can talk, and we do talk about a lot about the change in the technology. But the fundamental change is that all of that is driven by two things that are new. You have an entirely new class of users. You have an entirely new class of users that may not even know that they are using HPC. We call it implicit HPC. Anytime you need something that adds intelligence to a decision, right? I don't have to go start an MPI forest or ranked forest or whatever it's called today. I don't have to know how to provision a network. I don't have to understand job queues. I just go, hey, I need this answer that's going to need some fundamental compute in the back end, and it's going to predict something like, how much should I pay for an insurance premium for my next vacation? How likely is it to be used, right? It's implicit HPC. Those users don't care about HPC. They care that their answer is right and that HPC somehow has helped, right? It's really, from an Intel perspective, it's really the equivalent of HPC inside, right? The second thing is these users have very, very different expectations. They actually don't admire complexity. They don't admire something the more difficult it is. I know this is kind of gee, that's not true, but it is true, right? The economics of the world we live in today, where you bring up an application on a Friday afternoon, you deploy it over the web, on the cloud over the weekend, and then by Monday you tear it down, and you're hoping to hit somewhere between 5 and 15 million users, make 10 cents per use. That's the economics. That's the time constant in which these users use these systems, right? And hand in hand with that is developers. These are developers. In many cases, the users are the developers. We look at the maker community or others that go, I'm developing an application. I don't intend to create the next Microsoft or the next Oracle with this. I intend to capitalize on the now and here, and then I'll move on, right? I don't intend to become a PhD in computer science. I don't intend to actually ever learn those big words like Fortran and other things that scare me, right? I know Java. I know maybe Python. I know how to use libraries. I inherited some code from someone else, right? And I needed to run without having to modify it because they got it running to solve that part of the problem. That's the development speed, agility, and efficiency that's being asked for these kinds of applications to come online, to make their impact the economic value realized from it, and then torn down. Right? So in essence, when we talk about what's going to change and why, fundamentally, if the users of this capability and those that have to develop to provide the users with what they need didn't have almost a new generation genre or set of needs, HPC would have evolved the way it's evolved the last 30 years. Nothing to be ashamed about, but it would have evolved within the constraints of what we have accepted, in whether it's talking about hardware, whether it's talking about software, whether it's talking about application development, and everything else. So what is this coming to? This notion of the change driven by new users, new usages, demanding new capabilities. What is this going to cause for us? That's the fundamental question. And that was why I put the question mark. Because if we can answer that, there is an answer to that question that actually should make all of us smile. And there's an answer to that question that is actually not as positive for us as an industry moving forward. I always prefer having the happy answer, right? So I'm going to try and answer this question from the happy side of how you take on the story of these two worlds. This is the world we, collectively, have not only come to know and love, but this is the world you've created. We've created together, right? And I'm going to lay out, there's lots of attributes of it, but I'm going to lay out a few that is pertinent to this discussion here today. The first is, it's single tenancy at node. I mean, I'm going to lay out some things that are essentially almost so taken for granted, so intrinsically natural that when we say it, it feels like, oh yeah, that's true, right? Performance is king. And for that, there is a dominant logic that you have to code to bare metal, right? The third one is, we know we have to share, and there are multiple jobs running, but we understand how an HPC job manager works, and it's our friend because it actually understands this notion of deterministic compute and SLAs, and actually assures us that performance still stays king, right? It's created with that exact thing in mind. The fourth one is, it's a common operating environment, right? When I go, it's like a little bit like using PC technology in some ways. This is a Windows machine. I know if I have to install an application, it better run on Windows, right? This is how the system works, from the operating system to library tools to how I write code and compile on it. And in most cases, again, to support the performance is king and the particular distributed needs of high-performance computing applications, it's a purpose-built fabric. Right? I mean, it's a purpose-built fabric that understands that bulk synchronous computing does have a very, very important dependency on balance at the scale-out arena. Now think about the new world of the cloud, right? It's multi-user. Not only is it multi-users, potentially on a single node, but it's also shared with non-HPC usage. That is an important aspect to understand, that it is not just about accommodating HPC usages, but there may be some completely non-HPC usages that drive, in fact, may economically drive more of the value prop or more of the return on invested capital in that system. Flexibility and TCO are king. When you are at hyperscale, you have, and we've seen this as we worked with cloud service providers over the years, the infrastructure is their business. And the TCO of that business, maintaining the capability, the hyperscale capability at an affordable TCO is king. And they will actually go to great lengths to optimize down to silicon products what's necessary to have a set of workloads that they use run optimally from a TCO perspective. It's managed by a cloud orchestrator. This sounds like, hey, I just switched the name from HPC Job Manager to a cloud orchestrator. But it's much more fundamental than that. What it means is it's almost like an authorized domain discussion, if you go along with that analogy. right? It has to live in a world of multiple applications, some of non-HPC, under an orchestration regime that is optimizing, in many cases, for TCO, high utilization, right? So now there's this interesting technical dilemma of, does resource scheduling for the HPC job nest under an orchestrator, or is it the other way around? In fact, depending on how you answer that question, you may actually be answering whether you really have just an HPC system that you're putting some automation into its orchestration, or you actually have a multi-purpose cloud that is also very good at serving HPC. But that's a fundamental architectural decision. It's a user-defined operating environment. I started life as a system administrator, and I had this one thing written on my wall, which is, life would be sweet if I could just avoid turning on these computers, right? Can you imagine the complexity a cloud service provider, an infrastructure as a service provider has to provide when they know every user might bring in their entire operation, their operating environment, from application to operating system, all containerized, whether it's in a virtual machine or otherwise, right? All of the plethora of operating environments that not only have to be maintained, but has to be orchestrated and run fairly optimally for users to be happy with the experience. And then, most likely, a general purpose network. Ethernet, if you look at most of the large hyperscale installations, it's Ethernet, because at that scale, you're networking more than you're doing fabricking, right? I'm not sure that's a real term, but you understand what I mean. So if you have to bridge these two worlds, where each world has a very good reason for being the way they are, right? What would you do? And this is the challenge that we face as a community. If you have to bridge these two worlds, you have to preserve what's on the left of the foil, which is really the value proposition of a hyperscale infrastructure. What are those? It's automated. At that scale, if you're not automated in the orchestration, it simply won't fly. Whether it's changing topologies, to its provisioning, to its maintenance, right? You cannot avoid automation. Second is elastic. You actually have an elastic capacity from a user standpoint. Yes, your wallet will feel it, but generally, it's not a fixed capacity situation. Okay. Third, it's federated, right? There is a regime. It's not a fight for all, I came here first, I get most. It's a federated ecosystem on the machine. Without that, there's chaos. There's no quality of service for anyone. And of course, economically, you cannot maintain SLAs and actually run the cloud. Fourth is secure. It has to be secure. When you are bringing people onto the cloud and you are telling them that this is as secure as them running it on-premise, and by the way, you're saying that to two parties, each of which are competing viciously in the marketplace, trying to build products and services, you have to make security a fundamental value proposition. Integrity of the data, security of the computation. Those are two different things, but they're very related. The last is, you have to be cost effective. If you're successful at doing all the things on the above, you will have tremendous demand. And if you're not effective at scaling your capabilities in automation federation, you will simply not be a cost-effective provider. So in many cases, scale is your friend. In order to keep that friend a friend, you have to make sure you do the other things. Why do you do this? So this sounds horribly like hey, here's someone who doesn't understand HPC just doing a cloud service provider pitch. Right? It's not, because there's the plus on the right-hand side of the foil. While you build in these advantages of a cloud delivery model, you can't compromise on performance. You cannot compromise on performance. You cannot compromise for the user. You cannot compromise for the developer. The developer must still be able to see HPC, the infrastructure like they did, because there is tremendous amount of intelligence that is in how jobs are placed, how ranks are created, how parallelism is expressed. So that if that abstraction happens, you will lose the performance is king, or the developers or the application or even the infrastructure will fail to deliver that near bare metal performance. The second is developer efficiency, right? Honed skills, people who've learned to code in parallelism, people who've learned how to develop for a dedicated infrastructure in supercomputing, to come to rely on certain guarantees, certain, what I would call determinism. You have to maintain that. Just because it is a almost virtual infrastructure that they're coding to, or writing applications and deploying them for performance, you can't give that up, right? Third is quality of service. Yes, you can be part of a job queue. Yes, you're in a capacity supercomputer, but when you're running, you have a deterministic quality of service, or at least you expect it. From not just the hardware, but you also expect it from the whole system solution. Everything from managing the stochastic elements of OS jitter down to things like the order of execution in your hardware on floating point. But there is a quality of service that cannot be given up just because you're running. You can't pinpoint exactly the infrastructure you're running on, and that may change over time. The last is what I, kind of encapsulating it, is determinism and control. A dedicated infrastructure, in most cases, is under your control. That pertains to a lot of things around security, integrity, and costs of maintaining it and moving data to it. And it's also deterministic, relatively more deterministic than one where the grounds are shifting as transparently as possible, but still shifting under your feet, right? So if this is the challenge, what we believe central to this challenge is to make a consistent platform, right? And I'm coming at it from a tops-down perspective. I'm really coming at it from a usage and developer perspective, right? Versus, being Intel, you would expect my first answer would be, and you have to make the best, CPU or fabric or memory for it. In order for these worlds to be bridged, the top of the bridge is really this consistent platform. The one on the left is the cluster, as we know it, right? Starts with all of your infrastructure with high-performance components. Excuse me. Then you have the platform. The platform is really the infrastructure software, as well as all your messaging libraries, your runtimes, and your resource manager. And then you have applications, and you can see right away how much visibility the applications have on the platform, and the platform has to the underlying infrastructure, right? That's the world we've lived in. We've honed, we've optimized every component, and we have these highly capable, very balanced systems as a result in its use. Look at HPC in the cloud. It looks roughly the same. And it should in the, I'm a little colorblind. The top is orange and yellow, right, Alexis? Okay. I don't know if it's color blindness or lack of sleep, but they all look different to me. But those are designed to look the same. Because you know what? They may be exactly the same things that were running on the left. And in fact, they should be. The magic is in that extra layer that's added above what's called infrastructure as a service, which is this HPC provisioning layer. This is what then takes the view up north, or from the north, and translates it to the view that has to exist when infrastructure is a service, as in automated, federated, and orchestrated, right? And provides this notion of consistency to the yellow and the orange without sacrificing performance, right? So this is, it may sound like, hey, that's just a shim layer of software, right? How many times have I heard that? Yeah, it's a pretty damn important shim layer. And that is the layer at which we have to understand not only what the expectations of, say, MPI messaging libraries or whether running PGAS programming models, right, what those are, but also how to map them on to the hardware, not just in a static sort of way, but to the state of use of hardware at that point in time, right? So this is where we think is both the opportunity and the bottleneck. So I said, clouding the future question mark. A fair amount of that answering the question with a smile is being able to build this common orange and yellow, which, by the way, the industry's done the left-hand side for decades now, and taking all of those investments down to expertise and making it viable on the cloud by adding what I call the cloudification portion in the provisioning layer, right? So how are we doing it? We at Intel believe, we worked with our partners, many of you in the room, to actually build the ecosystem on the left or provide meaningful components as well as contributions to that ecosystem in the software layer. What we believe is we are on a path to extending that for the cloud through this consistent platform strategy of taking that work, the cluster, and essentially in a nutshell saying, you still have your cluster. It's virtual and it's running in the cloud. So you still develop code for it the way you did. You still deploy your application without wondering about the infrastructure and is it different because I'm going to a cloud versus where I developed it or I've previously ran it. And you get the performance that you're expecting from it, right? That is, as I said, the challenge of bridging the worlds, and that is the work we're doing through the Intel Scalable framework as we look at the demands of not only the classical HPC portions, but increasing the machine learning and AI portions of the workload, right? Our goal is it'll run from small clusters through supercomputers at all scales. It'll run compute and data-centric jobs. If it didn't, then we're bifurcating essentially the infrastructure. In many cases, compute and data is no longer two different silos. They're just different phases of an application and its needs. The third one is we are quite passionate about standards-based programmability. If this doesn't happen, what we've learned over the last 30 years of x86 is it becomes frightfully hard for not just developers, but an economically sustainable R&D OpEx in the application ecosystem, right? And innovation stalls, essentially. And the last one, consistent with what I've been saying, is this has to work both on-premise and in a cloud-based infrastructure, right? The first, if we just said on-premise, this is the work we've been doing for the last 20 years, along with all of us, right? What we are viscerally now focused on is adding the delivery vehicle of the cloud, understanding its unique requirements, and understanding the constraints which have to be obeyed for these applications to actually successfully deploy and grow in its usage. What does the Intel Scalable framework, system framework have? It's really a system framework. It's an architectural design philosophy. But what it really does is it supports three things: a hardware foundation, and I'll talk about it in a second, a software environment, which is really kind of the guts of the consistent platform piece, and then a very important set of developer tools that make not only the orange and yellow work on the non-cloud, on-premise side or the traditional side, but in the cloud as well. And most importantly, with as much transparency as possible so that it doesn't feel like you changed. If you look at the hardware foundation, about 5 or 6 years ago, you'd say, hey, there's something called the Xeon. We all know and love it. It runs a majority of the workloads in high-performance compute today. And it has a very impressive and repeatable and predictable cadence of innovation, from whether it's SSC to AVX1 to AVX256 to 512, memory bandwidth improvements. And in fact, our next generation, this is going to roll off my tongue after N sessions with marketing to get trained on this. Intel Xeon Scalable Processor. Did I get that right? All right. We haven't, it's shipping today. If you looked at the list, you'd see 3 of those. Can you say that fast enough, Alexis? Intel Xeon Scalable Processor. And it's already on the list, 3 systems, along with Intel OmniPath architecture. In fact, number 12 and number 13 systems on the list, on the top 500 list today, one is a Knight's Landing system, which is Xeon Phi. One's next generation, please say it with me, Intel, Xeon, Scalable, processor. Did you say it? Okay. So it's evidence that not only is OmniPath getting deployed successfully at scale, and people are actually having a very good experience out of it, but the next Xeon is ramping very, very quickly. And we'll have many more announcements after we actually announce the product later in the year. In addition, we have other portions of the portfolio in the hardware space, again, recognizing that workloads need workload-specific acceleration. One is the Lakecrest. This is the company we acquired, focused on AI, and in particular, deep learning. Right? And Lakecrest is the first generation ASIC that we are building, and it's specifically focused on state-of-the-art deep learning training performance. We also have the FPGAs, both as discrete from our Altera acquisition, but more importantly, we're also in the market with a very tightly coupled Xeon plus an FPGA that has higher performance, lower latency, and higher bandwidth into the FPGA, making it quite an attractive deal for, again, new emerging applications like inferencing, and also continuing to drive usage for certain applications well known in financial services and like. And then, of course, as the world moves to SSD and then to storage class memory, right? These are the next big innovations on the hardware side. The software environment, the HPC orchestrator and Lustre, you should all be familiar with. We continue to innovate in it to not only provide next generation capabilities around object-orientedness of things like storage, but also take the capabilities of the orchestrator into the cloud. Again, looking at that consistent platform strategy, how do we add in the features you need for orchestrator to instantiate a virtual cluster that can be consistent with a software-defined infrastructure that essentially is an orchestration regime by a particular cloud solution, right? We now have optimized frameworks. If you're in the area of deep learning and your application, the deep learning application, you're coding to a framework, whether it's Caffe, it's Tiano, Torch, TensorFlow, including the Intel framework called Neon, right? So all of this then become part of the software environment that gives you that consistent platform, a capable and a consistent platform across on-premise and cloud. And then there's developer tools. These are fundamental. Some of these like Intel MKL, the math kernel libraries, the Parallel Studio. This is well known to the HPC community, but a large part of our investment is actually going into build tools like data analytics. That's DAL. TAP is it's really an analytics platform. What it does is it not only brings together portions of the stack and the solution, but also adds data cleansing and other tools that a data scientist would want to use to quickly deploy an analytics solution. So for us, the Intel Scalable System Framework is no longer just about the pieces of software that you need to get the max performance or the max best experience out of a cluster or of a supercomputer. It is a mindset. It is how you plan to build, deploy, maintain, and write code for, whether you're doing that on-premise or these new applications and your interest in them is driving you to a cloud or a software-defined infrastructure. We believe this is the path that we must take collectively as a community and work together to instantiate that bridge. Without the bridge, it's two worlds. And neither world will quite be as effective, will grow as effectively and see the innovations without this bridge happening. So if you want to see some of what I've been talking about, some of the guts of what we've been talking about in terms of technology demos, and hear more than just me talk about, not just Intel even, talk about what we are doing here and why is it important, what we are doing here and why is it important, come to our booth. And with that, I'll stop, and I think we're done.